At this point, we've gone through the key components of both confidence intervals and hypothesis tests. And for the remainder of the course, we're going to be reiterating those key components as we do a number of different types of those two inference methods. Also, as a reminder, when I say inference method, I'm talking about a method where we take a sample and then make a judgment about the population, whether we're estimating it or answering a question about the entire population based on the results of a sample. So in this chapter, which is going to close out the 5th unit, we're going to focus on comparing two proportions because oftentimes when we have a population parameter, instead of comparing it to a fixed value like 25% or 1/6, we want to compare it to another population to see is it the same or is it different. So we're going to be doing confidence intervals, hypothesis tests, and the good news is that all of these tests are really similar with just minor differences. Mainly it's the standard deviation that changes. And in explaining this, I want you to think back to chapter 4, unit 4, in particular, combining random variables. So if we think back to unit 4, when we were adding or subtracting random variables, the means we would just add logically. Okay, if we were subtracting them, we would just subtract them logically. Standard deviations, on the other hand, weren't as logical. Okay, we couldn't just add or subtract standard deviations. In fact, we never subtract standard deviations. So instead, we would always add the variances. Okay, variance is the square of the standard deviation. And that's what we're going to be doing in this section. Once we start comparing two proportions, we need to get a combined standard deviation. So we have the first sample with its own standard deviation, and the second sample with its own standard deviation. So to combine these two standard deviations, we combine the variances. We add the two variances. So square the first, square the second, add them together, and square root it. Same thing we did back in Unit 4. Like I've mentioned, you really can't forget anything because it all comes back as we close out the course. Assumptions and conditions are the same with the unfortunate exception that instead of checking these for one sample, we have two samples in our problem. So we need to check randomization, 10%, and success fail for each of the two samples in our problem. In addition to that, there's a fourth condition we have to check. This is called the independent groups assumption. And basically what this is saying is that our one sample is independent of the second sample. The two groups we're comparing are independent of each other. So we're going to start with a confidence interval. So if these conditions are met, we're going to find a confidence interval for the difference of two proportions, and it's given by this equation here. So the point estimate is the difference of our two p-hats. Okay, it's always subtracted, never added. Critical z-score, just like we had before, and the standard error, as I just explained, adding the variances of each of those individual samples. For example, among 242 Cleveland area children born prematurely at low birth weights between 1977 and 1979, only 74% graduated from high school. Among a comparison group of 233 children of normal birth weight, 83% were high school graduates. Create a 95% confidence interval to find the parameter of interest, p at low minus normal. So we're going to do panic on this question. So define the parameters. There's two in this case. We're going to say PL represents the true proportion of Cleveland area children born at low birth weights who go on to graduate high school. And PN represents the true proportion of Cleveland area children born at normal birth weights who go on to graduate high school. Make sure you're specific with those parameters and really just copy them directly from the problem. A, assumptions. Randomization. Assume both samples were selected randomly and are representative of their respective populations. 10%, 242 is less than 10% of Cleveland area children that were born with a low birth weight. 233 is less than 10% of those born at a normal birth rate. Okay, we're checking all these conditions for both groups. Success fail, make sure you denote these as NP hat low and Q hat low. We check both of them and then do the same thing for the normal group. We expect at least 10 successes and failures in both groups. Now that we have a two-sample test or two-sample interval, we have to check the independent groups assumption. These two groups are independent of each other. The high school graduation rates for low birth weight children and normal birth weight children should not affect one another. Name the method. Back in chapter 19, we did a 1 proportion Z interval, and now we're adding a second sample, which makes this a 2 proportion Z interval. Write the interval. First, we want to find the standard error for the difference in these two population proportions. So we take the standard deviation for the first sample, standard deviation for the second sample, add them together, and square root it. We're adding the variances to combine these two standard deviations. We get 0.0374. Point estimate for the difference of the two proportions is just the low group minus the normal group. If you did this in reverse, that would be fine. It would just change the signs on our intervals from negative to positive, and that's okay. So here we have 0.74 to 0.83. We get negative 0.07. 1.96 is the critical z-score for a 95% confidence interval. And lastly, we're going to write a conclusion. The wording of this has to be specific. It's not quite as straightforward as it is when there's one sample. So both of these numbers are negative, which means when we did our interval, which we did in this order, low minus normal, we got negative numbers, which means this has lower rates than the normal group. Okay, if they were positive, it would mean the opposite. It would mean the low group had higher rates than the normal group. So when we write it out, we say we are 95% confident that the true proportion of high school graduates in the Cleveland area is between 16.3% lower and 1.6% lower for children with low birth weights compared to those with normal birth weights. It says lower here because they're both negative. Sometimes we have one that's negative and one that's positive, something like that, in which case this one would say lower, this one would say higher. So that was a confidence interval. Hypothesis tests in some ways are easier, in some ways are harder. One particular way that it's easier is that the null hypothesis for a two proportion test is always the same thing, and it's always stating that our two proportions are the same. There's no difference in the percent of high school graduation rates among like low birth weight students versus normal birth weight students. All right, so this will always be our null hypothesis. Okay, you could write it like that or like that for a two proportion test. For the entirety of any hypothesis test, we believe that's true. So we believe that these two groups have the same graduation rates for the duration of this test until we get to that p-value and it's small enough for us to reject it. Now, that being said, since we believe that these are the same, that the graduation rates are the same, any difference that we see in our samples of the p-hat1 and p-hat2, we initially attribute to just natural sampling variation, right? And because of that, we say that this is just a chance occurrence of different samples. So to get a more accurate representation of what the actual graduation rate is, we're going to throw all of those together and we're going to pool them, it's called, into one big proportion. So if they actually do all graduate at the same rates, which is what our null hypothesis says, which therefore we believe for the whole test, our p-hat's going to be more accurate if we take all of the graduates from the low group, all of the graduates from the normal group, and we add them together. And we divide that by the full sample size of both groups combined. This is called a pooled p-hat. And we're going to use this to find a standard error. Okay, so we put this in both of these fractions, pooled p-hat, pooled q-hat, divided by our first sample size. Same thing on the top of the second fraction, divided by second sample size. Let me show you what I mean as I work through this problem. Same context, it's asking, is there sufficient evidence to suggest that there's a difference in graduation rates between the two groups? It's no longer asking us to estimate the difference. Instead, it's asking us a yes or no question. Is there sufficient evidence to suggest there's a difference? Yes or no. This means hypothesis test instead of confidence intervals. We're going to do phantoms on this. Parameter is the same as the last problem. I'm going to skip over that, jump to hypotheses. Null hypothesis is always the same. There is no difference in these proportions. Any difference we see is natural sampling variation. Alternative, there is a difference. Now we're going to make a pooled p-hat. To make a pooled p-hat, we're going to take all the graduates from the low birth rate group and the normal birth rate group, combine them, and divide by our total sample size of both groups combined. We only do this for hypothesis tests, and the reason we do it is because the null hypothesis says these two proportions are the same. Any difference in the groups individually is just natural sampling variation. If we took larger samples, we would see those p-hats move together and become the same number. So combining them makes a larger sample, and larger samples are better. That's a better representation of an actual p-hat. So we're going to use that as our pooled group. Assumptions, these are the same as what we checked in the confidence interval, with the exception of success fail, because we would use this number just to make sure we have enough. We do, there are at least 10 successes and failures checked for both groups. And name the method. Last time it was a 1 proportion z-test. This time it's a 2 proportion z-test. Test statistic. We want a pooled standard error, okay, which means we're putting that pooled p-hat and pooled q-hat on top of both of these fractions with each sample size on the bottom. Okay, it gives us a standard error of 0.0378. We find our point estimate, the difference between those two groups, and it's always being compared to 0. So we're always subtracting 0. We really can just leave that part out. Right? Is this difference large compared to that standard deviation? So we divide it by that standard deviation. We get negative 2.38 as our test statistic. That's a z-score. On to the next step of phantoms. We take this z-score. We find the probability of it. Now keep in mind this is a two-tailed test. So when we look this up, we get a probability of being to the left of negative 2.38, which is 0.00045. But since our alternative hypothesis was that the difference between these two proportions is not equal to 0. Anytime we have a not equal to as our alternative, it's a two-tailed. We're just going to take whatever we get. We're going to mirror it on the other side here, which means there's another 0.0045 on that side. So we just double whatever we get from our normal CDF. So our p-value is 0.0009. Reject the null hypothesis since the p-value is small. There's sufficient evidence to suggest that there's a difference in graduation rates between the normal birth weight and low birth weight groups. If you're asked to interpret the p-value, if the null hypothesis is true and there's no difference in the graduation rates between the two groups, then the probability of seeing the observed difference or greater is 0.0009. You've seen this slide before. If you know it, you can end the video. If you're still having trouble with these last few steps, okay, the last two steps of phantoms, make a decision and state a conclusion, are always directly tied to your p-value. If the p-value is small, meaning below 5%, or whatever our alpha level is, we would reject the null hypothesis and say there's sufficient evidence to suggest that whatever our alternative hypothesis is true. If the p-value is not small, above 5%, or whatever our alpha level is, fail to reject the null hypothesis and say there's insufficient evidence to suggest that the alternative hypothesis is true. The M is always about the null hypothesis, either reject it or fail to reject it. The S is always about the alternative, either we have sufficient evidence to support it or we have insufficient evidence to support it.